Welcome to Quietly Made. I am so glad you have found your way here tonight. This is a space for the curious and the weary, a place where we explore the vast, invisible infrastructures of our world, while giving your mind the permission it needs to simply rest. Before we begin, I invite you to join our community by subscribing and leaving a comment. I often wonder where these stories find you tonight. If you feel inclined, please leave a comment sharing what part of the world you are in and the hour you are settling into sleep. It is a small way for us to feel the quiet connection of this community, scattered across different time zones, but sharing this same moment of rest. If you fall asleep, that is exactly what should happen. You are safe here. You can always come back tomorrow and pick up exactly where you left off. Adjust your pillow. Take a deep, slow breath in and let it out. Let your mind drift as we begin. The surface of the ocean conceals one of humanity's most essential infrastructures, invisible to those who cross above it, unknown to most who depend upon it daily. Beneath the waves, resting on seafloor terrain as varied as any continental landscape, lie cables that carry the flow of information between continents. A network more extensive and more critical than most people realize. The story of how these cables came to exist, how they function, and what they enable spans more than a century of engineering persistence, commercial ambition, and the gradual construction of a truly global communication system. Before these cables, the separation of continents by oceans meant that information could travel between them only as fast as ships could sail. A message sent from one coast to another took weeks to arrive, and the reply took weeks to return, creating delays that shaped every aspect of international commerce, diplomacy, and personal communication. The rhythm of global affairs pulsed slowly, constrained by the time it took for physical messengers to cross expanses of water that could not be bridged by any existing technology. The limitations were not merely inconvenient, but fundamental to how international relationships operated. A merchant shipping goods across an ocean made decisions based on information that would be weeks or months old by the time the goods arrived. A diplomat negotiating on behalf of their government worked with instructions that might have become obsolete during the time it took for the message containing them to arrive. Families separated by ocean crossings maintained relationships through letters that captured moments already receding into the past by the time they were read. The friction of distance created not just delay, but fundamental uncertainty about the state of affairs in distant places. The dream of instantaneous communication across oceans existed long before the means to achieve it became available. If electrical signals could travel through wires on land, carrying information at speeds that approached the speed of light itself, then surely similar signals could travel through wires laid underwater, connecting land masses separated by ocean. The concept seems straightforward. Manufacture a cable, lay it across the seafloor between continents, and transmit electrical pulses that could be decoded at the far end into meaningful messages. The reality would prove vastly more complex. The ocean itself presented obstacles that had no equivalent in land-based telegraphy. The depths were unknown in most places, measured only approximately, if at all. The pressure at those depths was immense, crushing anything not specifically designed to withstand it. The water conducted electricity, creating pathways for signals to leak from the cable before reaching their destination. Marine life, currents, seismic activity, and the simple abrasion of the cable against rocky seafloor. All of these represented threats to the integrity of a system that needed to function continuously, despite being inaccessible for inspection or routine maintenance once installed. The materials required did not exist in suitable form. Copper wire could conduct the electrical signals, but copper alone could not withstand seawater's corrosive effects or the mechanical stresses of installation and operation. Some protective coating was necessary, something that would insulate the conductor from the water while remaining flexible enough to be coiled aboard ships, strong enough to support its own weight during installation, and durable enough to last for years underwater without degrading. The search for appropriate materials would consume as much effort as solving the electrical and navigational challenges. The scale of the undertaking daunted even those convinced of its feasibility. A cable connecting continents would need to be hundreds or thousands of miles long, continuous from shore to shore, without breaks that would interrupt the electrical circuit. Manufacturing such lengths required industrial capacity and quality control beyond what existed for any other purpose. Transporting the cable to the installation site required ships with holds large enough to carry the enormous weight and volume. Laying the cable required controlling its descent to the seafloor while the ship moved forward, maintaining tension that kept the cable from tangling or breaking, while avoiding tension so great that it would snap under its own weight. The investment required would be substantial, far beyond what individuals could provide, and challenging even for the largest commercial enterprises. The risks were proportional to the scale. A cable that failed after installation represented a complete loss of the capital invested, with no salvage value and no way to recover the investment through partial operation. Investors would need to be convinced not just that the concept was sound, but that the specific implementation being proposed had reasonable probability of success. The technical demonstrations would need to be persuasive, the financial projections credible, and the people leading the effort trustworthy. Yet, the potential rewards justified the risks for those who could see beyond the immediate challenges to the world that successful transoceanic cables would create. The first enterprise to establish reliable communication between continents would have a monopoly, at least temporarily, on a service for which demand was certain and likely substantial. Governments would pay for secure, rapid communication with distant territories and diplomatic missions. Financial institutions would pay for market information that arrived ahead of competitors. News organizations would pay for reports that could be published while events were still developing, rather than weeks after outcomes had been determined. The commercial opportunity was clear to those with vision to perceive it. The strategic value of transoceanic communication extended beyond commercial applications into matters of governance and security. Nations with territories on multiple continents needed to coordinate administrative decisions, respond to local crises, and maintain control over distant populations and resources. The weeks of delay inherent in ship-based communication meant that colonial administrators operated with substantial autonomy, making decisions that might be countermanded by instructions that arrived too late to affect outcomes. Faster communication would allow more centralized control and more rapid response to situations requiring metropolitan involvement or approval. Military applications were obvious to those who considered them. Naval operations across oceans required coordination that was difficult when orders took weeks to reach fleet commanders and reports took weeks to return. The ability to communicate rapidly with ships at sea or with naval bases on distant coasts would provide strategic advantages in both peacetime operations and potential conflicts. Intelligence about enemy movements or intentions would be more valuable if it arrived while the information was still actionable, rather than after the situation had changed. The military establishments of major powers recognized these advantages and would become important customers for transoceanic cables once they existed. The technical problem of detecting electrical signals after they had traveled hundreds or thousands of miles through submarine cables required solutions that did not exist in land telegraphy. The signals attenuated, weakened as they traveled, absorbed by the cable's resistance and leaked to the surrounding water through imperfect insulation. By the time a signal reached the far end of a long cable, it might be barely distinguishable from the electrical noise that was always present in the system. Detecting these weak signals required sensitive instruments that could amplify faint pulses enough to be recorded or retransmitted without introducing so much noise that the signal was lost in the amplification process. The speed at which signals could be transmitted through submarine cables was limited by the cable's electrical properties in ways that were not initially understood. The cable acted as a capacitor, storing electrical charge that delayed how quickly voltage could change in response to transmitted pulses. This meant that rapid transmission would blur signals together, making them unreadable at the receiving end. The maximum transmission speed was inversely related to the cable's length. Longer cables required slower signaling to maintain adequate separation between pulses. This limitation would affect the economic viability of transoceanic cables by restricting how many messages could be transmitted per unit time, directly impacting revenue generation. The question of who would build and operate transoceanic cables involved both practical and political considerations. Private companies would seek profits and might charge rates that governments or public interest advocates considered excessive. Government operation might ensure lower rates, but would raise questions about preferential access, censorship, or surveillance. International cooperation would be necessary since cables connected sovereign nations, each with interests in regulating communication entering or leaving their territory. The regulatory framework would need to address these competing interests while allowing the system to function effectively. The reliability requirements for transoceanic cables exceeded what land telegraphy demanded. A break in a landline could be located and repaired within hours or days. with traffic rerouted through alternative paths if necessary. A break in a submarine cable might take weeks to locate and repair, requiring specialized ships to recover the damaged section from the seafloor, splice in new cable, and relay it. During the repair period, the cable would be completely out of service with no alternative path available until additional cables were installed. This meant that submarine cables needed to be far more reliable than land cables to provide acceptable service continuity. The environmental challenges went beyond the ocean itself to include the shore ends where cables landed. The surf zone where waves broke represented a particularly hostile environment. Violent water motion, shifting sands or rocks, and maximum exposure to marine-boring organisms that might damage cable sheathing. Getting cables safely from deep water across the surf zone to land-based stations required careful selection of landing sites and often required specialized protection methods: burial below the seafloor, routing through pipes or conduits, or armoring that could withstand the mechanical violence of breaking waves. The cultural impact of instantaneous transoceanic communication would be profound, though difficult to predict in detail. The psychological distance between continents would diminish when communication took minutes instead of weeks. Business relationships would operate differently when queries and responses could be exchanged within a day instead of requiring months for a complete exchange. The nature of news would change when reports of distant events could arrive, while outcomes were still developing, instead of after everything had been resolved. Family relationships across oceans would change when messages could be exchanged frequently, instead of through the lengthy letters that were the only previous option. The path from concept to reality would require solving problems in multiple domains simultaneously: materials, science, electrical engineering, naval architecture, manufacturing, finance, diplomacy, and organizational management. No single insight or invention would be sufficient. Success would come through the accumulation of solutions to hundreds of smaller problems, each necessary though not individually sufficient. The process would take years and would involve setbacks, failures, and expensive lessons learned through costly mistakes. But the direction was clear. Humanity would connect its separated land masses with cables that would carry information beneath the waves, creating a nervous system for the planet that would become more essential and more invisible with each passing year. The first attempts to create underwater telegraph cables worked from principles established in land telegraphy, but quickly encountered problems unique to the marine environment. Early experimenters wrapped copper wire in various insulating materials: rubber, tar-soaked cloth, layers of different compounds, seeking combinations that would protect the conductor from seawater while maintaining flexibility. Most of these early attempts failed within days or weeks as water penetrated the insulation, creating conductive paths that drained the signal before it could reach its destination. The failures provided lessons about what would not work, narrowing the range of approaches worth pursuing. Gutta Percha emerged as the most promising insulating material, a natural latex harvested from trees in Southeast Asia that had properties remarkably suited to submarine cable construction. When pure and properly applied, Gutta Percha resisted water penetration far better than other available materials. It remained flexible at normal ocean temperatures, allowing cables to be coiled and handled during installation. It could be extruded in continuous lengths around copper conductors, creating seamless insulation without joints where water might enter. The material was expensive and available only in limited quantities, but no alternative offered comparable performance for underwater use. The process of manufacturing cable required precision that pushed the capabilities of industrial processes. The copper conductor needed to be drawn to exact diameter. Too thin, and it would have excessive electrical resistance. Too thick, and it would be unnecessarily heavy and expensive. The Gutta Percha insulation needed to be applied in multiple layers, each heated and pressed to eliminate air pockets that would eventually fill with water. The thickness of insulation had to be sufficient to prevent electrical leakage while not adding so much weight that the cable could not support itself during installation. The balance of these factors required careful calculation and testing. Protective covering over the insulated core addressed mechanical threats that insulation alone could not resist. Iron or steel wires were wrapped around the core in helical patterns, creating armor that could withstand abrasion against rocks, resist biting or boring by marine organisms, and provide tensile strength during installation and operation. The number of armor wires, their diameter, and the tightness of the wrapping all affected the cable's properties, its weight, strength, flexibility, and cost. Different designs were appropriate for different situations, with heavier armor for shallow waters where threats were greatest and lighter construction for deep ocean where mechanical damage was less likely. The ships that would lay cable needed modifications beyond what commercial or military vessels typically possessed. Enormous storage capacity was required to carry miles of cable coiled in holds or on deck, arranged so it could pay out smoothly without tangling. Braking mechanisms were needed to control the rate at which cable left the ship, maintaining tension that kept it from falling too quickly and potentially breaking under its own weight. Steering systems needed to maintain precise course despite the drag of cable trailing behind. The crew required specialized training in handling cable, operating the laying machinery, and responding to problems that might arise during the delicate process of installation. Navigation posed challenges that routine sailing did not encounter. The ship needed to follow a predetermined path across hundreds or thousands of miles of ocean, with accuracy measured in miles, not the tens of miles that were adequate for normal navigation. Position needed to be determined frequently enough to make course corrections before the ship had wandered far from the intended route. Depth soundings needed to be taken continuously or at close intervals to ensure the cable was not being laid across terrain that might damage it or make future repairs difficult. The navigational technology of the era, celestial observation, dead reckoning, manual depth measurements, was barely adequate for these requirements and required careful attention from skilled personnel. Communication between the ship laying cable and the shore station where the cable terminated required methods that could operate over the partially completed cable. Test signals sent through the cable being laid allowed the shore station to monitor the electrical properties and detect problems, increases in resistance suggesting damage to the conductor, decreases in insulation resistance indicating water penetration. The ship needed to receive these reports to know whether to continue laying or to stop and investigate. Pre-arranged signal codes allowed basic communication, even when the cable's transmission characteristics were poor due to its incomplete state. Testing procedures developed through experience with early cable failures. Before installation, every section of manufactured cable underwent electrical testing to verify that it met specifications for conductor resistance and insulation quality. During installation, continuous monitoring watched for changes that might indicate damage occurring as the cable paid out. After installation, comprehensive tests measured the cable's end-to-end electrical properties and transmission capabilities. The testing equipment itself needed to be sensitive enough to detect subtle problems while being robust enough to function in shipboard or station environments where conditions were far from ideal laboratory settings. The first successful submarine cables connected points separated by relatively narrow stretches of water, channels between islands, short crossings between mainland and nearby territories. These installations served as proving grounds for techniques and technologies that would later be applied to transoceanic projects. Each short cable that functioned successfully built confidence and provided operational experience. Each failure revealed problems that needed solving before attempting longer, more expensive installations. The accumulated knowledge from these modest projects made the audacious transoceanic attempts seem feasible rather than purely speculative. The electrical theory underlying cable telegraphy was incompletely understood during early development, leading to surprises and misconceptions that affected design choices. The relationship between cable construction and signal propagation was complex, involving resistance, capacitance, and inductance in combinations that were difficult to calculate and harder to measure with available instruments. Theoretical physicists and practical engineers worked in parallel, sometimes with limited communication, developing understanding through both mathematical analysis and empirical observation. The synthesis of theory and practice gradually produced design rules that reliably predicted how cables would perform. Splicing techniques allowed repair of damaged cables and connection of sections manufactured at different times or locations. A successful splice needed to maintain the electrical properties of the intact cable: low resistance in the conductor, high resistance in the insulation, while having mechanical strength approaching that of undamaged cable. The splice also needed to be as smooth as possible to avoid catching during handling or creating stress concentrations that would become failure points. Achieving all these requirements required careful workmanship and quality control that could verify the splice met standards before it was buried under miles of water, where inspection would be impossible. The repeater stations that would eventually become necessary for very long cables were not part of initial designs because the technology to amplify signals without introducing unacceptable distortion, did not exist. Early transoceanic cables operated as single electrical circuits from shore to shore, with signals weakening as they traveled, but never being amplified en route. This meant the transmission speed was limited by how fast signals could be sent, while still being detectable at the far end. The limitation was fundamental to the electrical properties of the system and could only be improved through better cable design or more sensitive receiving equipment, not through any intermediate amplification. The economic model for submarine cables involved high initial capital costs, followed by relatively low operating expenses if the cable functioned properly. The revenue came from charging for each message transmitted, with rates reflecting both the costs of providing service and whatever the market would bear. Competition between cables on the same route would eventually drive rates down, but the first cable on a route could charge premium prices until competitors appeared. The financial success of a cable project depended critically on achieving reliable operation quickly after installation, so that revenue generation could begin before investors lost patience or ran out of capital. Insurance for submarine cable projects was difficult to obtain and expensive when available, because insurers had limited data on failure rates and because the magnitude of potential losses was large relative to premiums that customers would pay. Some projects proceeded without insurance, with investors accepting the full risk of total loss if installation failed. Others negotiated partial insurance that covered some, but not all of the capital at risk. The availability and cost of insurance affected which projects moved forward and influenced design choices. More conservative designs cost more initially, but reduced risk and therefore insurance costs. The regulatory environment for submarine cables was initially undeveloped because the technology was too new for existing laws and treaties to address. Questions about who owned cables in international waters, who had authority to regulate them, how to handle disputes about damage or interference, these lacked clear answers. Early operators negotiated individual agreements with the governments of countries where cables landed, establishing precedents that would eventually be codified into international law. The political dimension of cable projects was as important as the technical dimension, requiring diplomatic skill alongside engineering expertise. Labor relations in cable manufacturing and installation involved skilled workers whose expertise was essential, but whose working conditions were often difficult. Manufacturing required attention to detail and quality consciousness that not all workers possessed or maintained. Installation involved long voyages under conditions that could be dangerous and uncomfortable. The companies operating cable projects needed to attract and retain capable workers while managing costs in an industry where margins were uncertain. Strikes, accidents, and simple turnover of personnel could delay projects and increase costs, making human resource management a factor in project success, alongside technical and financial considerations. The public perception of submarine cables mixed admiration for the technical achievement with skepticism about reliability and concern about costs. Spectacular failures of early transoceanic attempts received wide coverage, creating impressions that the technology was not ready for commercial deployment. Successful installations received less attention unless they enabled some widely noticed communication: a news report, a market quotation, a diplomatic message that demonstrated practical utility. Building public confidence in submarine cables as reliable infrastructure rather than expensive experiments required consistent performance over extended periods, something that would take years to achieve. The refinement of cable design proceeded through systematic variation of construction parameters and observation of how each change affected performance and durability. Engineers tested different ratios of copper to insulation weight, finding that more insulation improved electrical properties but made cables heavier and more expensive. They experimented with armor wire configurations, discovering that certain wrapping patterns provided better protection against specific threats, while others offered advantages in flexibility or strength. Each iteration incorporated lessons from previous installations, gradually converging on designs that balanced competing requirements more effectively. The chemistry of Gutta Percha required careful control to maintain its desirable properties. Impurities in the raw material degraded insulation quality and accelerated aging. Processing at incorrect temperatures altered the molecular structure in ways that reduced flexibility or water resistance. Storage conditions mattered. Exposure to light, heat, or oxygen could damage Gutta Percha before it was even applied to cables. Manufacturers developed quality control procedures that tested raw material upon receipt, monitored processing conditions continuously, and verified the properties of finished insulation through sampling and testing. The consistency of cable quality improved as these procedures matured. Depth measurement technology advanced to meet the needs of cable route surveying. Earlier methods using weighted lines provided approximate depths, but were too slow and imprecise for detailed mapping of potential cable routes. Improved sounding machines, using piano wire instead of hemp rope, reached greater depths more reliably. Recording mechanisms captured depth profiles that could be analyzed to identify hazards, steep slopes, rocky outcrops, volcanic features that should be avoided. The accumulated depth data created increasingly detailed maps of ocean floor topography, serving scientific purposes beyond their immediate application to cable routing. Cable recovery and repair developed into specialized operations requiring purpose-built ships and equipment. Grappling hooks designed to snag cables on the seafloor had to be heavy enough to maintain bottom contact while being dragged, but not so heavy they could not be lifted when they caught the cable. The process of locating a break, narrowing down its position from electrical measurements, then searching the suspected area systematically could take days or weeks. Once recovered, the damaged section was cut out, new cable spliced in, and the repaired cable relayed. The entire process required calm weather and could be interrupted by storms that forced suspension until conditions improved. Manufacturing capacity expanded as demand for cables increased. New factories were built near ports where ships could be loaded efficiently. The machinery for applying insulation and armor was refined to increase production speed while maintaining quality. Workers became more skilled through experience, reducing defects and improving productivity. The supply chain for raw materials matured, with reliable sources for copper, Gutta Percha, iron wire, and other components. This industrial infrastructure represented substantial investment, but was necessary to support the growing network of submarine cables being installed worldwide. The electrical characteristics of installed cables changed over time as materials aged and as marine growth accumulated on the exterior. Insulation resistance gradually decreased as Gutta Percha absorbed trace amounts of water, or as chemical changes in the material created conductive paths. Marine organisms attached to cables sometimes created electrical anomalies by concentrating metallic elements from seawater. These changes were usually gradual enough that they did not impair operation significantly, but they required periodic monitoring to ensure cables remained within acceptable parameters. Long-term reliability depended on materials and construction methods that minimize these aging effects. Standardization of message formats and operating procedures improved efficiency and reduced errors. Codes were developed that represented common words or phrases with brief sequences of electrical pulses, allowing more information to be transmitted in less time. Operators trained to recognize these patterns by sound or by the appearance of recorded signals could transcribe messages more quickly and accurately than if each letter was transmitted individually. The standardization also allowed operators to move between different stations or cable systems without extensive retraining, creating a labor pool with transferable skills. The economic geography of cable routes reflected both technical constraints and commercial calculations. Cables followed great circle routes where possible, minimizing distance and therefore cost and signal attenuation. They avoided known hazards, volcanic zones, fishing grounds where anchors might snag them, areas with frequent seismic activity. They landed at points where physical geography provided some protection. Harbors, bays, locations with sandy bottom in shallow water that allowed cable burial. The pattern of cable routes that emerged connected major commercial centers along paths that balanced all these considerations, creating a network that reflected the priorities of the companies and governments funding the installations. Competition between cable companies on profitable routes drove technical innovation and price reductions. A second cable on a route broke the monopoly the first cable had enjoyed, forcing rate reductions to maintain market share. The pressure on prices created pressure on costs, encouraging efficiency improvements in every aspect of operations: manufacturing, installation, maintenance, and message handling. Some companies failed when they could not compete effectively, with their assets absorbed by more successful operators. The consolidation of the industry created larger companies with more resources for continued development and more diversified route portfolios that reduced risk. The training of cable operators became more formalized as the volume of traffic increased and as the consequences of errors became more significant. Schools taught telegraphy fundamentals, the specific codes and procedures used in submarine cable work, and the distinctive characteristics of receiving signals through long cables where distortion and noise degraded signal quality. Students practiced until they achieved speed and accuracy standards required for commercial service. The professionalization of the operator workforce improved service quality and reduced the frequency of errors that caused customer complaints or message delays. Maintenance scheduling balanced the cost of proactive inspections and repairs against the cost of failures that occurred between maintenance intervals. Cables in harsh environments, or those experiencing high failure rates, received more frequent attention. Cables with strong performance records and favorable environmental conditions could operate for extended periods without intervention. The maintenance strategy evolved as operational data accumulated, allowing more sophisticated analysis of failure patterns and causes. Predictive maintenance, based on early indicators of developing problems, became possible as understanding of failure mechanisms improved. Political disputes sometimes involved submarine cables, either as targets of deliberate damage or as subjects of disagreements about access and control. During conflicts, belligerents sometimes cut enemy cables to disrupt communications. Neutral countries objected when their cables were damaged as collateral effects of military operations. Disputes arose over rates, service quality, or preferential access to capacity. International law slowly developed frameworks for addressing these conflicts, but enforcement remained problematic when the parties disagreed about interpretations or when no effective mechanism existed to compel compliance with agreed principles. The relationship between cable companies and their customers evolved from a provider-client model towards something more like a utility relationship. Large customers negotiated volume discounts and priority service agreements. Governments used their regulatory authority to influence rates or service terms. Public interest advocates argued for universal access at affordable rates rather than market-based pricing that put costs beyond the reach of ordinary citizens. The cable companies navigated these pressures while attempting to maintain profitability sufficient to cover capital costs and fund continued network expansion. Technical documentation accumulated as each cable project generated records, route surveys, installation logs, test results, maintenance histories, operational statistics. This documentation served multiple purposes. It supported ongoing operations by providing information needed for maintenance and troubleshooting. It informed future projects by capturing lessons learned, and it served as legal records in disputes about performance or liability. The challenge was organizing this documentation so relevant information could be retrieved when needed, a problem that became more difficult as the volume of records grew with network expansion. The social impact of submarine cables manifested in changed patterns of international interaction. Business decisions were made with more current information about conditions in distant markets. Diplomatic negotiations proceeded with reduced delay between proposals and responses. News of distant events reached audiences while situations were still developing. Family communications became more frequent, though more abbreviated. Long letters gave way to telegrams that conveyed essential information in minimum words to control costs. The culture of communication adapted to the medium's characteristics, creating new conventions around what was appropriate for telegraph messages. Scientific study of the ocean advanced through knowledge gained during cable operations. Depth soundings created detailed profiles of seafloor topography. Recovery of cables from great depths brought up materials from the deep ocean, revealing organisms and sediments that had been inaccessible. Temperature measurements at various depths contributed to understanding of ocean structure and circulation. While these scientific benefits were incidental to the commercial purposes of cable projects, they represented valuable contributions to oceanography that would have been difficult to obtain through purely scientific expeditions without the resources and motivation that cable operations provided. The accumulated effect of improvements across all aspects of submarine cable technology was a system that became progressively more reliable, more capable, and more economically viable. Each generation of cables lasted longer, transmitted faster, and required less maintenance than its predecessors. The network grew denser as new routes were established and redundancy was added to important links. The cost per transmitted word declined, making cable services accessible to broader populations and supporting growing message volumes. The infrastructure that had begun as an uncertain experiment gradually matured into essential architecture of global communications, though its nature would continue evolving in response to new challenges and opportunities that emerged with changing technology and geopolitics. The core of every submarine cable began with copper wire drawn to precise diameter through dies that shaped the metal, while work hardening it to the required tensile strength. The drawing process pulled annealed copper through progressively smaller openings, each pass reducing diameter by a calculated amount, while elongating the wire. The process continued until the wire reached the specified gauge, thick enough to have acceptably low electrical resistance per unit length, but not so thick that weight and cost became excessive. The finished conductor needed to be straight, uniform in diameter along its entire length, and free from surface defects that might concentrate stress or create points where insulation adhesion would be compromised. The extrusion of Gutta Percha insulation around the conductor required heating the material to a temperature where it became plastic enough to flow, but not so hot that it degraded. The process fed the copper conductor through the center of an extrusion die, while simultaneously forcing heated Gutta Percha through the die opening, creating a concentric layer around the conductor. Multiple passes applied successive layers, each bonding to the previous one as it cooled, building up the required insulation thickness. The temperature, pressure, and speed of extrusion all affected the quality of the insulation. the absence of voids, the uniformity of thickness, the adhesion between layers. Maintaining these parameters within tight tolerances required constant attention from operators who adjusted the machinery in response to variations in material properties or ambient conditions. Testing the insulated core before armor application detected defects, while they could still be repaired relatively easily. Electrical tests measured resistance of the conductor and insulation resistance between conductor and water-filled bath surrounding a sample section. The tests needed to detect even minor imperfections because small defects would worsen over time once the cable was installed underwater, where pressure would force water into any opening in the insulation. Lengths showing inadequate insulation resistance were rejected, cut out, and the remaining sections spliced together. The testing was methodical and time-consuming, but essential for ensuring that only cable meeting specifications proceeded to the next manufacturing stage. Armor wire wrapping machines rotated multiple spools of iron or steel wire around the insulated core as it passed through the center of the machine, laying the wires in helical patterns at angles calculated to provide optimal protection and strength. The tension on each armor wire needed to be controlled. Too loose, and the armor would not adequately protect the core. Too tight, and the wires might crush the insulation or introduce residual stresses that would cause problems later. Different machines handled different cable diameters and armor configurations, from light deep-sea cables with minimal protection to heavy, shore-end cables with multiple layers of armor designed to withstand severe mechanical abuse. The serving of jute or other fibrous material between armor layers and over the exterior provided cushioning that prevented armor wires from cutting into the Gutta Percha when the cable flexed or when armor wires slid against each other under load. The serving also absorbed tar or other preservatives that protected the iron armor from corrosion and the jute itself from rot. The thickness and tightness of serving needed to be consistent along the cable length. Variations would create weak points or bulges that might catch on equipment during handling. The serving process used specialized machinery that wrapped the fibrous material at high speed while maintaining uniform tension. Cable tanks on board, laying ships, held the finished cable coiled in layers, with each layer separated from those above and below to prevent tangling. The bottom of the tank was cone-shaped, so cable would feed from the center of the coil, pulling smoothly as the ship moved forward. Water filled the tanks to keep the Gutta Percha insulation cool and to provide buoyancy that reduced the effective weight of cable stored in the tank. The arrangement of cable in the tanks required careful planning. The ship would lay cable in the order it was loaded, so the cable sections had to be loaded in reverse order of their position along the planned route. Getting this wrong meant the cable could not be laid without cutting and splicing to reorder the sections. Paying out machinery controlled the rate at which cable left the ship, using friction brakes that gripped the cable with force adjusted to maintain proper tension. Too little tension and the cable would fall too rapidly toward the sea floor, potentially piling up or tangling. Too much tension and the cable might break under the combined stress of its own weight and the brake force. The brake operators monitored the depth, ship speed, and rate of cable deployment, making continuous adjustments to keep these parameters in the correct relationship. The work required skill developed through experience and attention that could not lapse even briefly without risking problems that might take hours to resolve. Sheaves and guides directed the cable path from the storage tanks up to the deck and over the stern of the ship, their surfaces lined with soft materials that would not damage the cable covering. The path needed to avoid sharp bends that might kink the cable or stress it beyond safe limits. Each point where cable changed direction introduced friction that affected the tension throughout the system. The geometry of the paying out arrangement was carefully designed to minimize these effects while keeping the machinery compact enough to fit within the available deck space. Regular inspection ensured that sheave linings were not worn to the point where they might damage passing cable. Dynamometers measured the tension in the cable as it paid out, using the deflection of the cable's path over a suspended sheave to indicate the force. The measurement provided feedback to brake operators who adjusted brake pressure to maintain tension within safe limits throughout the varying conditions of depth and ship motion. Recording mechanisms traced the tension over time, creating permanent records that documented how the installation had proceeded. Analysis of these records after installation could identify sections where tension had been excessive, marking them as areas where the cable might be more vulnerable to failure and requiring closer attention during future maintenance. Electrical continuity testing during laying involved sending test signals from the shore station through the cable being laid and measuring their strength and character at the ship. Changes in signal strength indicated problems. A sudden increase in resistance suggested damage to the conductor. Decreased insulation resistance indicated water intrusion. And changes in capacitance revealed alterations in the cable's electrical properties. The tests ran continuously during laying, allowing immediate detection of problems so the crew could stop paying out cable and investigate before too much defective cable had been laid. The test equipment needed to be sensitive enough to detect subtle changes while being robust enough to function reliably despite shipboard vibration and environmental variations. Splicing machinery cut cable ends squarely, stripped insulation to expose the conductor, joined the conductors mechanically and electrically, then rebuilt the insulation and armor around the joint. The process required precision. Misaligned conductors created high-resistance connections. Inadequate insulation left vulnerable points where water could eventually penetrate, and poorly applied armor concentrated stress that could lead to mechanical failure. Splicing crews trained extensively because the quality of their work directly affected cable reliability. Each splice was tested electrically before the cable was relayed, verifying that it met specifications for resistance and insulation before committing it to the ocean floor. Buoys marked the positions where cable was temporarily suspended during splicing or repair operations, supporting the weight of cable hanging from the surface to the seafloor and indicating the location to other vessels that might otherwise accidentally damage the suspended cable. The buoys needed to be large enough to provide adequate flotation, yet manageable enough to be deployed and recovered by the ship's crew. Markers on the buoys identified them as supporting submarine cable operations, warning other vessels to keep clear. The buoy anchors needed to hold position despite currents and weather, while being recoverable when operations were complete. Grappling equipment for cable recovery used heavy iron hooks designed to drag along the seafloor and catch the cable when they passed over it. The grapnel was lowered to the bottom. The ship slowly moved across the suspected cable location, and the crew monitored tension in the grappling line for the sudden increase that indicated the hook had caught something. Distinguishing a cable catch from a rock or other seafloor feature required interpretation of how the tension changed. A cable produced a characteristic pattern as the grapnel pulled it upward from the seafloor. Multiple passes across the search area were often necessary before successfully hooking the cable, making recovery operations time-consuming and dependent on favorable weather throughout the process. Cable cutting machines severed recovered cable sections quickly and cleanly, important when weather was deteriorating and speed was essential. The machines clamped the cable securely, applied opposing forces that concentrated stress at the desired cut location, and completed the cut before the cable could twist or deform in ways that would complicate subsequent splicing. Portable machines could be operated on deck under whatever conditions prevailed, while more elaborate fixed installations in cable ships provided better control, but required bringing the cable to the machine's location. The choice of cutting method depended on circumstances, urgency, weather, the condition of the cable being cut, and the type of operation being conducted. Testing tanks at shore stations and aboard cable ships allowed inspection of cable sections under simulated operating conditions before installation. A coil of cable submerged in a tank of water at controlled temperature underwent electrical testing that measured how its properties would perform under actual service conditions. The tests identified manufacturing defects, verified that specifications had been met, and provided baseline data against which future measurements could be compared to detect degradation. The testing was destructive of time. Cable in tanks awaiting testing or undergoing tests was not being installed or earning revenue, so test procedures needed to be thorough enough to provide confidence while efficient enough to avoid excessive delay. Shore-end equipment included heavy tackle for pulling cable from ships across the surf zone to land-based cable houses, armored pipes or trenches that protected cable in shallow water from wave action and anchors, and vaults where the ocean cable connected to land lines. The transition from sea to land was one of the most vulnerable parts of the system, accessible to interference, exposed to forces from waves and currents, and subject to damage from storms that rearrange seafloor sediments. The design of shore-end installations required understanding of local conditions, wave climate, tidal range, sediment transport, and construction robust enough to withstand the worst conditions likely to occur during the cable's operational life. Multiple layers of defense, burial, armor, redundant routing, protected against the various threats this critical section faced. The diversity of cable designs in the early years created complications when cables from different manufacturers needed to be connected, or when repairs required splicing cable sections with different construction. The dimensions of conductors varied between suppliers. Insulation thickness followed different specifications. Armor configurations used incompatible wire gauges and wrapping patterns. Interconnecting these dissimilar cables required custom splicing techniques that added time and uncertainty to operations. The industry recognized that standardization would reduce these inefficiencies while creating economies of scale in manufacturing that would benefit all participants. International conferences brought together representatives from cable companies, manufacturers, and governments to negotiate standards that would apply across national boundaries. The discussions balanced technical optimization against the commercial interests of existing suppliers who had invested in particular designs and manufacturing equipment. Some proposed standards required minimal changes from existing practice and gained acceptance easily. Others demanded substantial modifications that would impose costs on manufacturers or make existing cable inventory less valuable. The resulting compromises reflected both engineering considerations and the political and economic power of different stakeholders. Conductor specifications standardized around a limited number of wire gauges selected to cover the range of applications from short local cables to transoceanic installations. Each standard gauge had defined electrical resistance per unit length, tensile strength requirements, and maximum allowable variation in diameter. The standardization allowed manufacturers to stock copper wire in standard sizes, reducing inventory costs and production delays. It allowed cable companies to specify requirements using standard designations that all suppliers understood identically. It simplified splice design because connections would join conductors of identical or compatible dimensions rather than requiring custom matching of dissimilar wires. Insulation thickness standards specified minimum dimensions for different cable applications based on the maximum voltage the cable would carry and the depth at which it would operate. Greater depths required thicker insulation to withstand hydrostatic pressure that could compress the insulation and force water through any imperfections. Higher voltages required thicker insulation to prevent electrical breakdown across the insulation. The standards included testing procedures to verify that manufactured cable met specifications and tolerance ranges that defined acceptable variations from nominal dimensions. Manufacturers who met these standards could be confident their products would be accepted by cable operators worldwide. Armor wire standards address the diameter, tensile strength, and coating of wires used in various armor configurations. The galvanizing or other protective treatment of armor wires was specified to ensure adequate corrosion resistance for the intended service life. The lay length, The distance along the cable for one complete helix of armor wire was standardized for different cable diameters to provide appropriate flexibility while maintaining protection. The number of armor wires in each layer was specified based on cable diameter and application, with heavier armoring for cables in fishing areas or shallow water where mechanical threats were greatest. Testing protocols standardized the procedures for verifying cable quality during manufacturing, before installation, during laying, and throughout operational life. The standards specified test voltages, current levels, duration of tests, and acceptance criteria. They defined how to measure insulation resistance, conductor resistance, and capacitance. They established procedures for detecting faults and for verifying that repairs met the same standards as original cable. The standardized testing meant that results from different facilities or operators could be compared directly, and that all parties shared common understanding of what constituted acceptable performance. Splice specifications standardized the mechanical and electrical requirements for joints between cable sections. The conductor connection needed to have resistance no greater than a specified percentage above the resistance of an equivalent length of continuous conductor. The insulation rebuild around the splice needed to withstand the same test voltages as intact cable. The mechanical strength of the completed splice needed to approach that of unspliced cable to prevent the splice from becoming a weak point. The dimensional envelope of the splice needed to be small enough to pass through paying out machinery without modification. These requirements ensured that splices did not create operational limitations or vulnerabilities. Message format standards defined the structure of transmitted communications, how addresses were specified, how message text was encoded, how special characters and numbers were represented, how error checking was implemented. The standardization allowed messages to traverse multiple cables operated by different companies without requiring translation or reformatting at each boundary. It enabled automated routing where messages could be forwarded toward destinations without human intervention at every station. It reduced training requirements because operators moving between different systems encountered familiar formats and procedures rather than having to learn unique conventions for each employer. Frequency allocation standards became necessary as cables began carrying multiple simultaneous transmissions using different frequency bands. The standards specified which frequencies were reserved for which purposes, how much frequency spacing was required between adjacent channels to prevent interference, and what power levels were permitted. The regulations needed to account for the electrical characteristics of submarine cables that made their frequency response different from landlines or radio systems. International coordination ensured that cables crossing territorial boundaries used compatible frequency assignments that would not create conflicts when signals from different national systems merged. Maintenance standards established schedules for routine inspections, testing intervals for various cable parameters, and criteria for when preventive repairs or replacements were necessary. The standards distinguished between cables in different service conditions. Those in harsh environments needed more frequent attention than those in benign locations. Heavily used cables required different maintenance approaches than lightly loaded ones. The maintenance protocols included record-keeping requirements that documented what work had been performed, what conditions were found, and what actions were taken. The accumulated maintenance records informed decisions about network investment and helped predict when cables would need major overhaul or replacement. Safety standards addressed both the electrical hazards that high-voltage cables presented and the mechanical hazards of cable handling operations. Grounding procedures prevented dangerous voltage accumulation during maintenance work. Lockout procedures ensured that cables could not be energized while personnel were working on them. Mechanical safety standards specified safe working loads for equipment, required safety factors in cable strength calculations, and mandated protective equipment for workers. Training requirements ensured that personnel understood hazards and knew proper procedures for working safely around cable systems. Documentation standards specified what information needed to be recorded about cable routes, installations, splices, and repairs. The standards defined map symbology for showing cable locations, formats for recording depth profiles, conventions for identifying splice locations, and systems for tracking cable sections by manufacturing date and origin. The standardized documentation allowed information to be shared between organizations and archived in ways that made it retrievable decades later when needed for planning new cables or investigating problems. The documentation standards evolved as new information technologies, photography, electronic data storage, geographic information systems, provided enhanced capabilities for capturing and organizing information. Quality assurance standards established certification programs for manufacturers, testing laboratories, installation contractors, and maintenance providers. The certifications verified that organizations had appropriate equipment, qualified personnel, and documented procedures that met industry standards. Audits confirmed that certified organizations actually followed their stated procedures and that their work product met specifications. The certification system gave cable operators confidence that contractors would deliver acceptable results and provided contractors with credentials that demonstrated their capabilities to potential customers. Interoperability standards ensured that equipment from different manufacturers could work together within integrated cable systems. The electrical interfaces between cables and terminal equipment were standardized so that cables could be connected to any compatible terminal without custom matching circuits. The signaling protocols were standardized so messages transmitted by one manufacturer's equipment could be received by another's. The physical interfaces, connector types, mounting dimensions, cable terminations, were standardized to allow substitution of equipment from alternative suppliers without requiring redesign of installations. The interoperability reduced customer dependence on single suppliers and encouraged competition that drove quality improvements and cost reductions. Terminology standards created common vocabulary for cable systems so that technical discussions used terms with agreed meanings. The standards defined terms for cable components, installation operations, types of faults, test procedures, and performance parameters. The terminology standards were particularly important for international operations, where participants spoke different languages. Standardized technical terms could be adopted into multiple languages with consistent meanings, facilitating communication despite language barriers. Technical publications, specifications, contracts, and operating procedures all benefited from terminology standards that eliminated ambiguity and ensured mutual understanding. Training standards specified the knowledge and skills required for various roles in cable operations and established competency assessment procedures that verified individuals met these requirements before they were certified for specific responsibilities. The standards defined curricula for formal training programs, prerequisites for advancement to more responsible positions, and continuing education requirements to maintain certifications. The training standards improved workforce quality and mobility. Workers certified under standardized programs could move between employers with confidence that their qualifications would be recognized and that they possessed the capabilities needed for their assigned roles. The accumulated effect of standardization was a global submarine cable system where components, procedures, and practices were sufficiently harmonized that the system functioned as an integrated whole despite being built and operated by many independent organizations. The standardization reduced costs through economies of scale and interchangeability. It improved reliability by codifying proven practices and establishing minimum quality levels. It facilitated international cooperation by providing common frameworks that transcended national boundaries. The standards themselves continued evolving as technology advanced and as operational experience revealed opportunities for improvement. But the principle of standardization as a foundation for the industry became firmly established and would guide development of subsequent generations of cable technology. The gradual displacement of earlier communication methods by submarine cables happened with little fanfare, noticed primarily by those directly affected, the shipping companies whose message-carrying business declined, the investors who had financed ship-based communications seeing their returns diminish, the workers whose livelihoods depended on the older systems. For most users of communication services, the transition was simply a matter of faster delivery at eventually lower cost, a change that seemed natural and inevitable once the option became available. The infrastructure that had sustained transoceanic communication for centuries quietly faded as the new infrastructure assumed its functions. Financial markets adapted first because the value of timely information was clearest there. Price movements in one market that could be arbitraged against prices elsewhere became known within minutes instead of weeks, eliminating opportunities that had previously existed for traders with patient capital and fast ships. The synchronization of markets across oceans increased as information flow accelerated, creating more globally integrated pricing, but also transmitting shocks more rapidly. The financial community quickly came to depend on cable communications to the point where disruptions that would have been unremarkable in the ship message era became serious operational crises. Diplomatic communications shifted to cables gradually, with official messages sent by secure encrypted cable, while less sensitive correspondence continued via diplomatic pouches on ships. The speed of cable communications changed the pace of negotiations and the autonomy of distant representatives. Instructions could arrive quickly enough that local diplomats had less discretion to act on their own judgment. Responses to developing situations could be requested and received within timeframes that made centralized decision-making practical. The nature of diplomatic work changed as the balance shifted from independent representatives adapting policy to local conditions toward field implementation of decisions made in capitals with rapid communication back to center. Commercial correspondence followed patterns determined by cost and urgency. High-value transactions justified cable costs. Routine business continued by mail. The briefness that cable rates encouraged created a telegraphic style. Compressed language, abbreviated references, implicit context that contrasted with the detailed letters that ship mail had carried. Business relationships adapted to this new communication style, with understandings established through quick exchanges rather than through the extended correspondence that had previously been necessary. Some lamented the loss of nuance and personal touch, while others appreciated the efficiency and the ability to conduct more transactions in less time. News organizations were among the heaviest users of cable capacity, driven by competition to publish reports of distant events before rivals. The economics of news gathering changed as the advantage went to organizations that could maintain correspondence in multiple locations connected by cable, rather than to those that could arrange fastest ship transport of reports. Coverage patterns shifted toward events in cable-connected locations, while areas lacking cable access received less attention regardless of their intrinsic importance. The geography of news became the geography of cable infrastructure, influencing public awareness of global events in ways that reflected the communication network's architecture as much as the significance of the events themselves. Personal messaging remained limited by cost. Cable rates made casual conversation prohibitively expensive for most individuals. Family communications by cable consisted of urgent notices, births, deaths, crises, conveyed in minimum words to control costs. The emotional content of these compressed messages was different from the letters they supplemented rather than replaced. Letters continued to carry the details of daily life. The extended narratives that made absent loved ones present through description and reflection. Cables announced events that required immediate knowledge or response. The two forms of communication coexisted, serving different purposes, with cables handling time-sensitive information while mail carried everything else. The workforce implications of the transition from ship-based to cable-based communications affected different groups unevenly. Cable operators needed training in telegraphy that was distinct from the general clerical skills that had been sufficient for managing ship-carried correspondence. The specialized knowledge commanded premium wages that attracted capable workers, but the total number of positions was smaller than the workforce that had been employed in the ship message system. Messengers who had carried physical documents found their services less in demand. Shipping companies that had relied on message-carrying revenue needed to adjust business models as that income declined. The transition created winners and losers, though the benefits to communication users generally outweighed the costs to displaced workers. Regulatory attention increased as cables became infrastructure that governments considered essential. The ability to censor, monitor, or control cable communications became matters of state interest. National security considerations prompted requirements for domestic routing of certain messages, or restrictions on foreign ownership of cables landing on national territory. The international character of cables complicated regulation, since most cables crossed multiple jurisdictions with potentially conflicting requirements. Treaties and bilateral agreements addressed some conflicts, but tensions persisted between sovereign control and the practical requirement for international cooperation that cable operation demanded. The cultural impact of accelerated communication manifested in changed perceptions of distance and foreignness. Places connected by cable felt more accessible, less remote, even though physical travel times remained unchanged. The psychological distance diminished as information about distant places became more current, and as interactions with people in those places became more frequent. Some cultural distinctiveness eroded as fashion, ideas, and commercial practices diffused more rapidly across cable-connected regions. Others argued that cable communications preserved cultural connections that would have attenuated through isolation, allowing diaspora populations to maintain ties with origin countries more effectively than would have been possible through mail alone. Investment patterns responded to the improved information flow that cables provided. Capital could move more quickly to opportunities in distant markets when information about those opportunities arrived while they still existed. Risk assessment improved when current, rather than dated information, informed decisions. The integration of capital markets accelerated, though political barriers and currency concerns remained obstacles to complete integration. The cable network became financial infrastructure whose reliable operation was essential to the functioning of international finance, making cable outages matters of commercial significance that affected far more than just the inability to send messages. Strategic military planning incorporated the assumption of cable communications for command and control, logistics coordination, and intelligence distribution. The vulnerability of cables to cutting became a consideration in war planning. Denying enemy communications while protecting one's own cables became objectives in themselves. The peacetime value of cables for maintaining contact with distant military installations and for coordinating naval operations made them militarily significant infrastructure whose protection during conflicts became necessary. Some military planners recognized that dependence on cables created vulnerabilities and maintained alternative communication capabilities. But the advantages of cable communications were substantial enough that military operations integrated them deeply. Technical employment patterns shifted toward the specialized knowledge required for cable operations. Telegraph operators formed a distinct occupational category with training, terminology, and working conditions particular to their trade. Engineers specializing in electrical systems found employment in cable companies that landline telegraph companies also needed, but in different balance of skills. The manufacturing sector employed workers in cable production who needed different capabilities than those manufacturing other products. The emergence of this technical workforce preceded broader electrical engineering as a distinct profession, with cable technology serving as a training ground for electrical expertise that would later be applied in other domains. The transition in international timekeeping accelerated as cables made possible the rapid distribution of precise time signals. Prior to cables, each locality maintained its own time based on local solar observations with no particular need for synchronization with distant places. Cable communications created advantages to coordinating time across regions, scheduling messages, coordinating business hours, enabling time-sensitive transactions. The technical capability to distribute time signals via cable preceded social acceptance of standardized time zones by years, but the cables provided the infrastructure that made standardization practical when it eventually occurred. Educational curricula adapted to include training in telegraphy and electrical principles that cable operations required. Technical schools produced graduates with the specialized knowledge that cable companies sought. Universities began offering courses in electrical engineering, partly in response to the demonstrated commercial value that cable systems created. The educational pipeline that fed technical talent into the cable industry represented a feedback loop. Successful cable operations created demand for specialized knowledge, which justified educational programs, which produced graduates who enabled further cable development and operation. The aesthetic and cultural representation of cables as symbols of modernity and progress appeared in literature, art, and public discourse. Cables featured in fiction as plot devices, enabling rapid communication that affected story outcomes. Visual artists depicted cable laying as heroic technical achievement. Public celebrations marked the opening of new cable routes as occasions of national pride and technological triumph. The cultural meaning attached to cables exceeded their purely utilitarian function, making them representations of human capability to overcome natural obstacles and to connect what geography had separated. The long-term effect of this transition was the establishment of cable communications as invisible infrastructure, whose presence was noticed mainly through its absence when failures occurred. The novelty wore off as reliability improved, and as generations grew up, never having known a world without rapid transoceanic communications. The system that had seemed miraculous to those who remembered ship-based messaging became mundane to those who had never experienced the delays it replaced. This normalization of the remarkable was perhaps the most significant cultural impact, the transformation of what had been impossible into what was taken for granted. Barely a generation after the first successful cables began operation, the infrastructure had become part of the assumed background of modern life, essential yet largely invisible to those it served. The shore stations where cables terminated served as the interface between submarine systems and terrestrial networks, housing equipment that translated between the electrical characteristics of ocean cables and landlines. The buildings themselves were constructed with attention to protection against both environmental threats and unauthorized access. Thick walls provided thermal mass that moderated temperature fluctuations affecting sensitive equipment. Multiple power sources ensured operations could continue during electrical grid failures. Security measures prevented tampering with or damage to the cable connections and terminal equipment that represented critical points of vulnerability in the communication system. The landing sites for cables required careful selection based on multiple criteria. The approach from deep water needed to be relatively smooth, without rock outcrops or steep slopes that would stress the cable during laying or subject it to abrasion from bottom currents. The beach itself needed to provide stable ground for the cable house and reasonable protection from storm waves that might damage shore-end installations. Proximity to population centers and existing telegraph networks was desirable, but needed to be balanced against the technical requirements of a suitable landing location. Some of the finest landing sites were in remote locations, requiring construction of substantial landline networks to connect them to major communication routes. The cable route from deep ocean across the continental shelf and through the surf zone used progressively heavier armor as water depth decreased and exposure to mechanical threats increased. The transition from light deep-sea cable to heavy shore-end cable occurred at depths where anchors, fishing gear, and wave action began to present significant risks. Splices joining these different cable types needed to transition smoothly between the different constructions while maintaining electrical continuity and mechanical strength. The shore-end section often was buried in trenches plowed into the seafloor sediments or laid in protective pipes through the most hazardous zone immediately offshore. Repeater stations for very long cables that required signal amplification were built at carefully selected locations along the route. typically on islands where undersea cable sections could land and connect to amplification equipment before continuing underwater to the next segment. The repeaters needed reliable power supplies, often requiring dedicated generating equipment where grid power was unavailable. The stations required skilled operators to monitor the repeater equipment and the cable sections it connected, to detect problems early and to coordinate with other stations along the route. The locations chosen for repeater stations balanced technical requirements against the practical considerations of provisioning and staffing installations in what were sometimes quite remote locations. Test facilities at shore stations included sensitive galvanometers that detected minute electrical currents, resistance bridges that measured cable impedance precisely, and specialized apparatus for identifying the location of faults from the electrical signature they created. The test equipment required careful calibration and skilled interpretation of readings that could be affected by temperature, electrical noise from nearby equipment, and the inherent variability in cable electrical properties. The test operators developed expertise in distinguishing real faults from artifacts of the measurement process and in extracting maximum information from the limited signals that long cables provided. Power supply systems at shore stations originally used batteries that provided the direct current required for telegraph signaling, with the batteries recharged by local generators or grid connections where available. The battery banks were substantial, rows of cells in glass jars requiring periodic maintenance to check electrolyte levels, clean corrosion from terminals, and replace cells that lost capacity. Later installations used rectifiers to convert alternating current from generators or grid to the direct current needed for signaling. The power systems needed to be reliable because any interruption stopped communications, requiring redundant capacity and automatic switching that maintained power supply despite component failures. Cable vaults protected the transition from submarine cable to landlines, providing physical security and environmental protection for connections that needed to be accessible for maintenance, yet protected from damage and unauthorized access. The vaults contained terminal blocks where submarine cable conductors connected to landline circuits, grounding systems that protected equipment from lightning or electrical faults, and test points that allowed measurement of electrical parameters without disrupting service. The interior environment was kept dry through drainage systems and sometimes active dehumidification, preventing corrosion that would degrade electrical connections. Archives at shore stations preserved records of cable installation, testing, maintenance, and operational performance that documented the cable system's history. The archives contained route charts showing cable paths and water depths, splice logs recording the location and date of every splice in the system, test records tracking electrical parameters over time, and repair logs documenting problems and the work performed to address them. These records served operational purposes, guiding repair efforts diagnosing problems, planning future maintenance. They also served historical purposes, capturing the evolution of the cable system and preserving institutional memory that would otherwise be lost as workers retired or moved to other employment. The landline networks connecting shore stations to population centers required their own infrastructure of poles or underground conduits, intermediate relay stations, and connections to other telegraph networks. The land portion of international cable routes sometimes exceeded the submarine cable length and required comparable investment and maintenance. The integration of submarine cables into broader communication networks required technical compatibility, the same signaling methods, similar electrical characteristics, standardized message formats, and organizational coordination between the cable companies and the landline operators whose networks provided the final delivery of messages to recipients. Weather monitoring at shore stations and along cable routes served both operational and safety purposes. Weather conditions affected cable laying operations, with rough seas preventing safe handling of cable and forcing delays until conditions improved. Storm surges could damage shore-end installations if not adequately protected. Temperature variations affected cable electrical properties in measurable ways that needed to be accounted for in testing and fault location. The cable companies maintained weather records that contributed to broader meteorological knowledge while serving their immediate operational needs. Support vessels dedicated to cable maintenance and repair represented substantial capital investments that needed to be positioned where they could respond quickly to cable failures. The ships required specialized equipment, cable tanks for carrying repair cable, grappling gear for recovering damaged sections, splicing equipment for making repairs, navigational instruments for finding cable locations. The crews needed training in cable handling and repair techniques that were distinct from ordinary seamanship. The vessels spent much of their time idle, waiting for repair calls, making their operation expensive per repair, accomplished, but necessary to maintain acceptable cable system availability. Communication between shore stations and cable ships during laying or repair operations used a variety of methods depending on the installation era and available technology. Early operations relied on prearranged signal codes transmitted through the cable being worked on. Later, wireless radio allowed direct voice communication when ships were within range of shore stations. The coordination required for successful cable operations depended on reliable communication that could convey technical information, operational decisions, and status updates between ship and shore, despite the distances and conditions involved. Warehouses near shore stations stored spare cable, splice materials, and equipment needed for repairs and maintenance. The inventory needed to include adequate quantities of cable, matching the types used in the routes being supported, since cable from different manufacturers or production runs might not be compatible for splicing to existing installations. The storage facilities needed to protect materials from environmental degradation, moisture, temperature extremes, sunlight that could damage cable or supplies before they were needed. Inventory management balanced the costs of maintaining adequate stocks against the risks of not having critical materials available when needed for time-sensitive repairs. Training facilities for cable operators and technicians provided instruction in both theoretical knowledge and practical skills. Students learned electrical theory, cable construction, signaling methods, message handling procedures, and fault diagnosis. Practical training used retired cable sections that allowed students to practice splicing, testing, and fault location without risk to operational cables. The training also covered organizational procedures, record keeping, and the administrative aspects of cable operations. Graduates entered the workforce with baseline competencies that employers could build upon through on-the-job experience with specific equipment and procedures used in different parts of the cable network. Administrative headquarters for cable companies coordinated operations across multiple cables and shore stations, managed financial and regulatory matters, negotiated with customers and other carriers, and planned network expansion and upgrades. The headquarters required staff with expertise in multiple domains: engineering, finance, law, diplomacy, logistics. The management challenges of operating international infrastructure, crossing multiple jurisdictions with complex technical requirements, exceeded what most other enterprises of the era encountered. The organizational capabilities developed by cable companies in managing far-flung operations with high reliability requirements would later be applied in other industries facing similar coordination challenges. International coordination mechanisms allowed cable operators to cooperate on matters of mutual interest, despite being competitive on many dimensions. Industry associations shared technical knowledge, coordinated standards development, and represented common interests in dealing with governments and international organizations. Bilateral agreements between operators established interconnection points, revenue sharing for messages traversing multiple cables, and mutual assistance during emergencies. The tension between competition and cooperation was managed through a combination of formal agreements and informal relationships among technical and management personnel who recognized that some level of coordination served everyone's interests. The accumulated infrastructure, shore stations, cable ships, test equipment, landline connections, warehouses, training facilities, and administrative organizations represented investment comparable to the submarine cables themselves. This terrestrial infrastructure was essential for the cable network to function, yet it was less visible than the dramatic engineering of the cables themselves. The system required both the underwater technology that captured public imagination and the mundane but necessary supporting infrastructure that received less attention but was equally critical to providing reliable communication services that justified the enormous capital investment the entire system represented. The completion of cables linking major continents created, for the first time, a communication network that spanned the globe, connecting locations separated by vast distances into a system where information could flow between any 2 points within hours rather than weeks. The network did not form all at once, but accumulated through decades of incremental expansion, each new cable adding connections that increase the system's reach and redundancy. The result was infrastructure that made possible forms of international coordination and interaction that had been impractical or impossible when communication required physical transport of messages. Financial markets integrated more tightly as prices in different regions could be arbitraged within the timescales that made such operations profitable. Commodities traded in multiple markets moved toward price equilibrium faster when information about supply, demand, and prices could traverse oceans quickly. Currency exchange rates reflected conditions across connected markets rather than being determined purely by local factors. The synchronization was not perfect. Local conditions still mattered, and time zone differences created trading cycles. But the degree of integration increased substantially compared to the era when price information arrived only as fast as ships could carry it. Corporate management structures adapted to the possibility of maintaining closer coordination between headquarters and distant operations. Companies with facilities on multiple continents could exercise more centralized control when instructions could reach remote locations quickly and when reports could return with similar speed. The organizational forms that emerged reflected this enhanced connectivity: less autonomy for distant managers, more frequent reporting requirements, greater standardization of practices across locations. The cable network enabled more globally integrated companies, though it did not determine their structure. Organizational choices still reflected management philosophy, competitive strategy, and the specifics of different industries. Diplomatic communications via cable allowed governments to respond to international crises with coordination that would have been impossible in the ship message era. Alliances could be consulted and positions coordinated during rapidly developing situations. Negotiations could proceed with representatives remaining in communication with their capitals rather than having to act on their own judgment for weeks between instructions. The impact on international relations was subtle but significant. Crises that might have escalated while slow communications prevented coordination could potentially be managed through rapid consultation, though the same rapid communication also allowed conflicts to develop and escalate faster when parties chose confrontation over resolution. News gathering became truly international as correspondents in cable-connected locations could file reports that reached publication within hours of events occurring. The coverage patterns shifted toward locations with good cable connections, while events in poorly connected regions received less timely attention, regardless of their intrinsic importance. The public's awareness of world events was shaped by the cable network's geography. Areas with many cables and good connectivity were overrepresented in news coverage, while poorly connected regions were underrepresented. This bias in coverage influenced public opinion and policy priorities in ways that reflected infrastructure as much as the significance of events. Scientific collaboration accelerated as researchers could correspond rapidly about observations, experiments, and theories. Astronomical observations requiring coordination between distant observatories became practical. Seismic data from earthquakes could be shared quickly enough to contribute to understanding of how seismic waves propagated through the Earth. Meteorological observations from around the globe could be assembled into weather maps that showed atmospheric conditions over vast areas. The cable network became scientific infrastructure that enabled research requiring global coordination. Though the cost of cable communications limited how much scientific traffic the network carried compared to commercial and governmental messages. Migration patterns were influenced by the ability to maintain contact with family in origin countries through cable communications supplementing mail. The psychological distance of emigration decreased when urgent messages could be exchanged quickly, even if routine correspondence still relied on mail. Some potential emigrants were more willing to relocate when they knew they could maintain contact, while others who might have emigrated chose to remain when improved communications allowed them to participate in opportunities across oceans without permanently relocating. The net effect on migration patterns was complex and varied by specific circumstances, but the availability of rapid communication was one factor among many that influenced these significant life decisions. Emergency coordination improved when natural disasters, shipwrecks, or other crises could be reported immediately to distant authorities who might provide assistance. Rescue operations could be mounted more quickly when alerts arrived via cable rather than waiting for ships to carry news. Medical experts could be consulted about treating unusual conditions when descriptions could be transmitted and advice received within timeframes relevant to patient care. The humanitarian benefits of rapid communication were sometimes substantial, though they were less visible than the commercial and political applications that generated most of the cable traffic and revenue. The military significance of cable communications extended beyond routine coordination to include intelligence gathering and operational security. Messages sent via cable were vulnerable to interception at cable stations or through unauthorized tapping of cables, creating security concerns that affected what information governments were willing to send via commercial cables. Code systems provided some protection through obscuring message content, but the awareness that cable communications might be compromised influenced both what was sent and how it was expressed. The vulnerability of cables to cutting during conflicts made them both valuable assets to protect and tempting targets to attack, introducing cable security as a dimension of military planning. Economic development patterns were influenced by cable connectivity, with well-connected regions having advantages in commerce, finance, and access to information that poorly connected areas lacked. Port cities with cable landings attracted business that valued communication access. Financial centers with the best connections became more dominant in international finance. Manufacturing regions with good cable access could coordinate with distant markets and suppliers more effectively than less connected competitors. The cumulative effect was that cable infrastructure contributed to geographic patterns of economic activity, not as the sole determining factor, but as one element among many that influenced where different activities located. Cultural exchanges accelerated, though the high cost of cable communications limited the volume of purely cultural traffic. Artistic communities in different regions remained primarily connected through mail and through physical travel, but cable communications allowed coordination of exhibitions, performances, and publications that would have been more difficult with slower communications. The movement of cultural workers between regions was facilitated by the ability to maintain professional contacts via cable. The net effect on cultural exchange was less dramatic than on commerce or governance, but still represented an incremental increase in the rate of cross-cultural interaction. Educational exchanges benefited from cable communications that allowed coordination of student travel, verification of credentials, and arrangements for studies abroad. Universities in different countries could correspond about research collaborations and faculty exchanges. Scientific societies could coordinate conferences and publications. The academic world became more international as communication barriers diminished, though language differences, travel costs, and institutional inertia remained obstacles to collaboration that cables alone could not eliminate. Public health coordination improved as disease outbreaks could be reported quickly to international health authorities, and as advice about prevention and treatment could be disseminated to affected regions. Quarantine measures could be implemented based on current information rather than waiting for ships to bring news of epidemics weeks after their onset. Medical knowledge developed in one region could be transmitted to others facing similar health challenges. The cables contributed to the emergence of international public health cooperation that would eventually develop into formal organizations and treaties, providing the communication infrastructure that made such cooperation practical. Environmental monitoring gained capabilities from cable communications that enabled coordination of observations across vast distances. Ocean temperature measurements, reports of unusual weather patterns, observations of natural phenomena, all could be shared more rapidly than when mail was the only option. The scientific understanding of global systems benefited from the ability to assemble datasets from dispersed locations, though the cost of cable communications limited how much data could be transmitted, and the scientific use of cables remained a small fraction of their total traffic. Labor movements used cable communications to coordinate across national boundaries, sharing information about organizing efforts, strikes, and labor conditions. International labor organizations could maintain contact between their sections in different countries, though the cost of cables limited such use mainly to urgent or high-priority communications. The ability to coordinate internationally gave labor movements capabilities they had previously lacked. though governments and employers also used cables to coordinate responses to labor actions, creating a more level playing field rather than decisively advantaging either side. The philosophical implications of this global connectivity were contemplated by those who recognized that human civilization had crossed a threshold. Information could now flow around the planet at speeds approaching the physical limits imposed by the speed of electrical signals in cables. The barriers that geography had imposed on human interaction since the species emerged had been dramatically reduced, if not eliminated. The world had become smaller in a very real sense, not physically, but in terms of the time required for communication between any two locations. This compression of distance through technology had precedence in roads, ships, and railroads, but the submarine cable network achieved a degree of compression that was qualitatively different from previous advances. The long-term implications for human civilization were difficult to predict, but it was clear that the world connected by cables would evolve differently than it would have without this infrastructure. The invisible web beneath the oceans had become part of the nervous system of an emerging global society whose final form remained uncertain, but whose existence was no longer in doubt. The submarine cable network represented a peculiar form of infrastructure, invisible to most who benefited from it, buried beneath waters that few would ever traverse, yet essential to the functioning of systems that shape daily life for millions. This invisibility created a disconnect between the importance of the cables and public awareness of them. Most people who sent telegrams across oceans gave little thought to how those messages traveled, just as they gave little thought to how water reached their taps or how streets bore the weight of traffic. The cables were infrastructure in the purest sense, background conditions that enabled other activities, noticed primarily when they failed. The dependence on this hidden infrastructure created vulnerabilities that were not always appreciated by those whose activities relied upon it. A cable failure could disrupt commerce, delay diplomatic communications, prevent news from reaching publication, and sever contact between distant family members. The concentration of traffic on a limited number of cables meant that damage to a major route affected many users simultaneously. The time required to repair cables, days or weeks of locating breaks, recovering damaged sections, splicing in replacements, and relaying repaired cable, meant that disruptions could be prolonged. The system was robust in the sense that alternative routes usually existed, but the alternatives might have limited capacity or might require routing through jurisdictions that raise security or cost concerns. The ownership and control of cable infrastructure reflected broader patterns of economic and political power. The nations and companies with capital and technical capacity built the cables and operated them according to their interests. The routes chosen connected places that the cable operators considered commercially or strategically valuable, while locations that lacked such value remained unconnected or poorly served. The pricing of cable services reflected both the costs of providing them and the market power that operators possessed. Regulation attempted to balance private interests against public needs, but the effectiveness of regulation varied by jurisdiction and by the political influence that cable operators could muster. The question of who could access cable communications and on what terms had both practical and ethical dimensions. The cost of sending messages excluded much of the global population from using cables for anything beyond the most urgent communications. The ability to read and write was prerequisite to using text-based communication, further limiting access. Some governments restricted who could send or receive certain types of messages, imposing censorship or surveillance that affected both content and the willingness of people to use cables for sensitive communications. The cable network theoretically connected the world, but in practice, access was unequally distributed by wealth, literacy, location, and political freedom. The environmental impact of submarine cables was minimal compared to many human activities, but not zero. Cable laying disturbed seafloor sediments along routes. The cables themselves became artificial structures that marine organisms colonized, potentially affecting local ecology. Derelict cables abandoned after failures or obsolescence remained on the seafloor indefinitely. The scale of these impacts was small relative to fishing, shipping, or coastal development, but they represented humanity's extending reach into environments that had been largely untouched. The cables were artifacts of human technological capability, resting in the deepest parts of the ocean, testimony to both ingenuity and to the drive to connect that seemed fundamental to human nature. The labor that maintained the cable system was skilled, but often undervalued by those who benefited from its results. Cable operators worked in conditions that required sustained attention and precision, monitoring signals, transcribing messages, detecting faults, coordinating repairs. The work was mentally demanding, but not physically difficult, and the people who performed it were essential to the system, yet often invisible to those whose messages they handled. Cable ship crews worked in conditions that could be dangerous, handling heavy equipment in weather that sometimes made operations hazardous, spending weeks at sea during major repair operations. The functioning of the cable network depended on these workers maintaining standards despite conditions and compensation that did not always reflect their criticality. The security implications of cable communications extended beyond military applications to include economic espionage, political intelligence, and the potential for manipulation of information. Messages could be intercepted at cable stations by personnel with access to traffic or by unauthorized tapping of cables. The content of encrypted messages might be protected, but the fact that communication occurred between particular parties could itself be valuable intelligence. The vulnerability of cables to physical attack made them potential leverage points in conflicts. Cutting enemy cables disrupted their communications, while protecting one's own cables became a defensive priority. The dual nature of cables as both enablers of communication and potential weapons created complex strategic calculations. The psychological impact of instant communication across vast distances was difficult to quantify, but seemed real to those who reflected on it. The world felt smaller when one could send a message across an ocean and receive a reply within hours. The barriers that distance had imposed on human relationships diminished, though they did not disappear. The cost and formality of cable communications meant they supplemented rather than replaced slower forms of contact. The experience of receiving urgent news from distant places via cable, of learning within hours of events that affected one's life occurring thousands of miles away, created a sense of connection and vulnerability that had not existed when such news arrived only after delays that provided time for emotional preparation. The question of whether the cable network represented progress or merely change without clear direction to improvement was debated by those who thought about such things. The benefits were evident: faster commerce, quicker coordination of activities, more timely news, ability to maintain contact across distances. The costs were less obvious, but included the expense of building and operating the system, the disruption to communities near shore stations, the environmental impacts, however minor, and the subtle ways that rapid communication changed the pace and character of life. Whether the overall effect enhanced human flourishing or simply accelerated activities without making them more meaningful was a question without empirical answer. The democratization of long-distance communication remained incomplete despite technical capabilities that could have extended access more broadly. The cost structure of cable operations made it difficult to offer service at rates that most people could afford for routine communications. The concentration of cable landings in major commercial centers meant that populations distant from these nodes faced additional costs to access the cable network. The literacy and language barriers excluded many from participation, even where physical access existed. The cable network was in principle global, but in practice served primarily the commercial, governmental, and educated populations of connected regions. The relationship between cable communications and social change was complex and bidirectional. The cables enabled certain forms of international coordination that would have been impractical otherwise, facilitating the emergence of more globally organized institutions in commerce, governance, and other domains. But the cables themselves were products of social organization. They required capital accumulation, technical education, international cooperation, and legal frameworks that were themselves results of social development. The cables both enabled and reflected the emergence of more integrated global society, making it difficult to separate their role as cause from their nature as effect. The temporal experience of cable communications differed from both the immediacy of face-to-face conversation and the contemplative quality of letter writing. Cable messages arrived quickly, but not instantly. There was delay in transmission, processing, and delivery that created a particular rhythm of exchange. The cost per word encouraged brevity that eliminated the elaboration that made written correspondence rich with context and nuance. The formality of cable communications, the involvement of operators, the public nature of transmission through commercial services, the permanent record, made them different from casual conversation. The result was a mode of communication with its own conventions and constraints that users adapted to, but that also shaped what could be effectively communicated. The aesthetic of cable technology, the utilitarian design of cable ships, the functional architecture of shore stations, the industrial processes of manufacturing, reflected values of efficiency and practicality over beauty or grandeur. There was a certain stark beauty in the mechanical simplicity of cable drums or the geometric precision of cable routes on charts, but these were incidental to function rather than intentional aesthetic choices. The cable network was engineering infrastructure whose appearance reflected the priorities of those who built it: durability, economy, performance. The lack of ornament or artistic expression was itself a statement about what mattered in industrial modernity. The knowledge systems required to build and operate cable infrastructure were increasingly specialized and technical, creating communities of experts whose understanding was opaque to outsiders. The mathematics of electrical transmission, the chemistry of insulation materials, the metallurgy of conductors and armor, the navigation required for cable laying, each required training and experience that most people lacked. This specialization was necessary given the complexity of the technology, but created dependencies on technical elites whose expertise gave them power over infrastructure that affected many. The democratic governance of technical systems became challenging when the knowledge needed to understand them was accessible only to specialists. The long-term trajectory of cable technology pointed toward increasing capacity, reliability, and eventually decreasing cost, following patterns common to infrastructure development. But the specific path was uncertain. Would cables continue to dominate long-distance communications, or would alternative technologies emerge that would displace them? Would the network continue expanding to serve more locations, or would it consolidate around major routes? Would ownership remain private, or would cables be nationalized or placed under international control? These questions could not be answered definitively, but the directions seemed toward cables becoming more deeply embedded in the fabric of global communications, rather than being displaced by fundamentally different approaches. The philosophical question of whether connecting the world more tightly was inherently good remained open. The connections enabled beneficial coordination, but also transmitted shocks and crises more rapidly. They allowed cultural exchange, but might also enable cultural domination. They supported commerce, but also facilitated exploitation. They enabled communication, but perhaps at the cost of making silence and disconnection more difficult to maintain for those who valued them. The cable network was morally neutral infrastructure that could serve many purposes, and its ultimate contribution to human welfare depended on how it was used rather than on its mere existence. The world connected by submarine cables would be different from the world that preceded them, but whether that difference represented progress remained a matter of values and perspective rather than objective fact. The evolution of submarine cables would continue along trajectories established by decades of incremental improvement, with each generation of technology building upon the foundations laid by its predecessors. The basic concept, conducting electrical signals through insulated wires laid across the seafloor, would persist even as the details of implementation changed. The improvements would come through better materials that resisted degradation longer, through more sophisticated signal processing that extracted more information from limited bandwidth, through more efficient manufacturing that reduced costs, and through operational experience that improved reliability and reduced the frequency of failures requiring expensive repairs. The capacity of cables to carry information would increase through techniques that allowed multiple signals to share the same physical conductor without interfering with each other. Frequency division methods would allocate different frequency bands to different communication channels, effectively multiplying the number of simultaneous conversations a single cable could support. The development of these multiplexing techniques required advances in electronics that could generate, transmit, and receive signals at different frequencies while maintaining adequate separation to prevent crosstalk between channels. The economic benefits of increased capacity were substantial. More revenue could be generated from existing cables without the expense of laying additional ones. The materials science of cable construction would advance as new synthetic materials offered advantages over natural Gutta Percha or traditional armor wire configurations. Plastics with superior electrical properties and environmental resistance would eventually replace Gutta Percha, though the transition would be gradual as manufacturers gained confidence in the longevity of synthetic insulation. Armor materials would evolve toward alloys that provided better corrosion resistance or higher strength-to-weight ratios. The outer serving might incorporate materials that resisted marine-boring organisms more effectively, or that signaled the presence of cables to help prevent accidental damage from anchors or fishing equipment. The route planning for new cables would benefit from improved knowledge of seafloor topography and geology. More detailed mapping would identify optimal paths that avoided unstable sediments, volcanic zones, or areas of intense seismic activity. The selection of routes would increasingly incorporate environmental considerations, avoiding sensitive ecosystems where possible, or designing cables to minimize impact where avoidance was impractical. The balance between technical optimization and environmental protection would become more explicit as awareness of human impacts on ocean environments increased, and as regulations required consideration of environmental factors in infrastructure development. The installation techniques would improve through experience and through technological advances in navigation and cable handling. More precise positioning would allow cables to be laid along planned routes with greater accuracy, reducing excess cable length and avoiding hazards more effectively. Improved weather forecasting would allow better timing of installation operations to avoid periods when conditions would be unfavorable. The cable ships themselves would evolve toward more specialized designs optimized for cable operations, rather than being adapted from general-purpose vessels. The professionalization of cable-laying crews would continue, with training programs and certification systems ensuring consistent competency levels. The maintenance strategies would shift toward more proactive approaches as the costs of failures decreased relative to the costs of preventive maintenance. Regular inspection of critical cable sections using remote vehicles would detect developing problems before they caused complete failures. Partial upgrades of cable sections experiencing accelerated degradation would extend overall cable life. The replacement of entire cables would be scheduled based on condition assessment rather than waiting for catastrophic failures. The economic calculation would favor prevention over repair, as the value of uninterrupted service increased relative to the costs of proactive maintenance. The regulatory environment would likely become more complex as cables became recognized as critical infrastructure requiring oversight to ensure reliable operation, fair access, and alignment with national interests. International coordination would be necessary to address cables crossing multiple jurisdictions and to prevent conflicts over cable routes, landing rights, and operational practices. The balance between competition that drove efficiency and cooperation necessary for system-wide reliability would require ongoing negotiation among cable operators, governments, and international bodies. The regulatory frameworks would need to adapt as technology changed and as the strategic importance of cables evolved. The question of alternative technologies that might eventually displace cables would remain speculative, but worth considering. Radio communications offered the potential to transmit across oceans without physical infrastructure vulnerable to damage or requiring expensive installation. The limitations of radio, limited capacity, vulnerability to interference, inability to provide the security and reliability that cables offered, suggested that radio would supplement rather than replace cables for the foreseeable future. Other technologies might emerge that would change this calculation, but based on existing knowledge, cables seemed likely to remain essential infrastructure for transoceanic communications for decades to come. The expansion of cable networks to serve regions not yet connected would continue as economic development and political changes created demand in new markets. Remote islands, developing coastal nations, and regions that had been excluded from early cable routes would gain connections as the economics of serving them became favorable and as their strategic or commercial importance increased. The pattern of expansion would reflect both market forces and governmental policies that might subsidize cables serving national interests, even when purely commercial calculations would not justify them. The resulting network would be denser and more globally distributed than the cable systems of earlier eras. The integration of cables into broader communication networks, that included landlines, radio links, and whatever new technologies might emerge, would require standardization of interfaces and protocols that allowed seamless routing of messages across different media. The cables would become one element in heterogeneous networks rather than standalone systems, with traffic flowing across whichever paths offered the best combination of cost, speed, reliability, and security for particular applications. The technical challenges of this integration would be substantial but solvable through the application of engineering expertise and international cooperation. The economic model for cable operations would evolve as competition intensified and as technological changes affected both costs and capabilities. The era of monopoly profits on initial routes would give way to more competitive markets where multiple cables served major routes and where pricing reflected costs plus modest returns rather than whatever the market would bear. The commoditization of basic communications capacity would drive cable operators to differentiate their services through reliability, security features, or specialized services that commanded premium pricing. Some operators would fail when they could not compete effectively, with their assets acquired by more successful competitors or nationalized by governments seeking to maintain service. The workforce implications of advancing technology would include both displacement of some traditional roles and creation of new specialized positions. Automated systems would reduce the need for some operator positions while increasing demand for engineers who could design, install, and maintain more complex equipment. The skills required would shift toward higher technical sophistication, potentially creating challenges for workers whose capabilities matched earlier technology, but who struggled to adapt to new systems. Training and education programs would need to evolve to prepare workers for the changing demands of cable operations and to provide pathways for existing workers to develop new competencies. The environmental accounting of cable systems would become more comprehensive as understanding of ocean ecosystems improved and as the cumulative impact of human activities in the ocean became more apparent. The industry would face pressure to minimize the environmental footprint of cable installation and operation, to remove derelict cables that no longer served useful purposes, and to avoid sensitive habitats when routing new cables. The costs of these environmental measures would need to be absorbed by operators or passed along to customers, potentially affecting the economics of cable projects in ways that would influence which routes were developed and which remain proposals. The security dimensions of cable infrastructure would remain important as cables continued to carry sensitive communications and as their vulnerability to physical or electronic attack persisted. The protection of cables would require both physical security measures, surveillance of landing sites, patrols of critical cable routes, hardening of shore stations, and electronic security, encryption of traffic, authentication of users, detection of unauthorized access attempts. The balance between security and the operational efficiency that made cables commercially viable would require ongoing attention, particularly as the sophistication of potential threats increased. The social implications of ubiquitous global communications enabled by mature cable networks would continue unfolding in ways difficult to predict completely. The ability to communicate instantly with anyone anywhere might affect how people thought about distance, community, and identity. The exposure to diverse perspectives and information from around the world might influence cultural development and political attitudes. The dependence on communications infrastructure for economic and social participation might create new forms of inequality between those with reliable access and those without. The long-term effects would emerge gradually and would interact with other social changes in complex ways. The ultimate question of what this global communications infrastructure meant for humanity, whether it represented an unambiguous advance, a mixed development with both benefits and costs, or a change that was essentially neutral in its implications for human flourishing, could not be answered with certainty. The cables enabled connections that many found valuable, supported activities that generated wealth and knowledge, and contributed to a more integrated global civilization. They also consumed resources, created new vulnerabilities, and changed the pace and character of life in ways that some experienced as loss rather than gain. The assessment depended on values, on what aspects of human existence one considered most important, and on how one weighed near-term effects against long-term implications that remained uncertain. What was clear was that the submarine cable network had become part of the permanent infrastructure of modern civilization, as essential and as invisible as any other foundation upon which contemporary life was built. The cables beneath the oceans would continue to evolve, would be supplemented by new technologies, might eventually be replaced by fundamentally different approaches to global communications. But for the foreseeable future, they would remain critical threads in the fabric that held the connected world together. The story of these cables, how they came to exist, how they function, and what they enable, was a story of human ingenuity applied to the challenge of overcoming the barriers that nature imposed on communication. It was a story that continued to unfold with each new cable, each technical advance, each expansion of capacity, adding another chapter to the ongoing narrative of how humanity connected itself across the distances that geography had created. And so, the narrative of this assembly comes to its quiet conclusion. Whether you are still awake, or whether you have already drifted into a deep and peaceful sleep, know that you are exactly where you need to be. The world is vast, but tonight, its systems are simply the backdrop to your rest. Thank you for joining me here at Quietly Made. Rest now. Join us again tomorrow. Good night.